Hello guys and welcome back. So we left off from this state where we are getting all kinds of interesting results, and at the moment we're just transforming the constraints with the RBD object. You can see it's accumulating over and over and over, and the reason for that is because we are doing this over and over and over, and this is a recursive process, and we don't want that. We don't want that to happen. The other thing that's happening is these constraints are stretching, and that's going to mess with the anchor point, which should always be set at the center. If we look here, see how the anchor point is not in the center anymore. It's getting far and further away, and we have to have always the anchor point be the middle, the center of the primitives. So I'm going to do that. I'm going to use a primitive node, and I'm going to scale them to make sure that they always both points are always colliding and at the same position. Let's hit play. Okay, so it's better. The anchor point is, you see the geometry is not going crazy, and we are still going to have to fix a few more things. So the other thing is, this process is cumulative. It's adding over and over, and again we're doing this every frame. And the reason, the way to fix that is by, after we do this transformation once, we want to freeze these guys, okay, like we're doing now. We want to apply the transformation back. The same thing that we did here, we want to inverse it. And if you guys remember, we are creating a 4x4 matrix in these constraints, okay, and that attribute, the reason I put that is so that I can apply back this transformation. So I'm going to simply multiply V back by that matrix, and it's called trans matrix. Okay, and instead of applying it again, we want to apply the inverse, and this is going to put everything back in place the way it was. And with matrices, you see here it gave us an error. The reason for that is because Houdini doesn't know if it's a 3x3 matrix, if it's a 4x4, if it's a float or a vector, especially with matrix primarily, and quaternions. So I'm gonna type in 4 to make sure that we explicitly set the data type. Now if we hit play, it's better. It's not going back to the original position. See, it's holding up. And we still have one more thing to fix. And if you guys remember from the, actually we can take a look at that now. If I go back here and play this, and let's untemplate this. It's happening here. You see these guys are stretching. Okay, we don't want just the transformation to be applied to the constraint. We also want to give them a new orientation attribute, which Bullet will look for. Now the way I know these things is they're all mentioned in the documentation. So Bullet and Dobbs, they look for these guys. Okay, and specifically what we're interested in is in this area. So an orient attribute is a quaternion, which represents only the rotation information. We have a 4x4 matrix which contains translation, scale, and rotation, and we just have to extract the rotation from there and convert it into a quaternion. Now the rotation can be described using a 3x3 matrix. So first we need to convert the 4x4 matrix into a 3x3 matrix, and then convert that into a quaternion, and that's going to be our new orient attribute. And so let's do that. Let's go back. And we've done the inverse transformation here, which is great. And the next thing we want to convert the 4x4 into a 3x3. Now I'm going to create a 3x3 matrix. I'm going to call it rot matrix, and we're going to use this syntax, which is a bit weird, but the way to convert a 4x4 into a 3 is using parentheses matrix 3 and then space and then the name of the matrix, which is this. I'm gonna type in 4 just to make sure that it works. So now we've converted the 4x4 into a 3x3 matrix, and then we're going to convert that into a quaternion. Now to do that, we're going to use the quaternion expression, and then we're going to give it the matrix, which is rot matrix. Okay, but we don't want this exact orientation. We actually want the inverse of that. So I'm going to invert the rotation matrix, and then we're going to store this as an orient attribute. Now the orient attribute is a quaternion, and to create this quaternion type attributes, we're going to prepend it with a P, with the letter P, and that's going to create a 4 float attribute. See here it says quaternion. Okay, so that's what we need to do, and let's go back and let's hit apply, and there we go. That's our system working nicely. Now remember we talked about the anchor points, okay, and that's this is something very important. If we place them in the center, it's going to give us a different result. It's going to give us more resistance because the objects are going to be colliding with each other. I'm also going to go to the RBD object and make sure it's set to boxes so that the collision geometry is more accurate, just for illustration purposes. And instead of using the point method, I'm going to generate between the centroid of the pieces, and then we scale those back so it's only up 1 point. And let's go back here, let's hit play, and now we have a different result. Okay, and this collision, this intersection here, is actually caused by the various things, primarily the collision padding. Let's set this to 0.001, and let's set this to 0.05, and let's increase the substeps. Bullet solver, set this to 40 and 40, and lower this, and see, now we have much more accurate result. And again, the higher the constraint iteration, the more stable it's going to be and the better the system is going to look, and that's how you get metal deformation. Now this is going to be used in our system, but we're going to mix it with a few other things. I'm going to continue setting this up using a small example to illustrate the idea and explain a few more Vex code, but overall this is the idea. We first import the geometry. It's very, very simple. The RBD, we import the constraints, okay, we extract the transformation, which is stored as a prim it's a prim intrinsic attribute, so it's not visible here, but it's called the packed full transform, which contains the 4x4 matrix. We apply that to the points to transform our constraints. We scale them down to 0, so the anchor point is always constant, and then we apply back the inverse transformation, and then we generate the orient attribute so that bullet doesn't try to go back to its original orientation, which caused this. If we try it again, it's working here, but it's going back. Yeah, the issue is not very visible in this example, but we need to always provide the orientation. And the quaternion is, we extracted the rotation matrix from the full transform matrix and then converted that into a quaternion and applied the inverse of that, and that's how we get this. Cool. So in the next video I'm gonna explain a few more Vex code that we'll need to use for the workshop, and then we're gonna move on to the full scene and set up the constraint there. Thank you guys for watching, and see you in a bit.